Woohoo! We are live. This is Math 40, Elementary Algebra, and this is 2.6, and we're going to get started on some problem solving. So these are going to be word problems, and we are going to be solving them for the most part with charts. So this is a particular type of problem solving. And for the most part in this section, these are going to be problems known as mixture problems. Now, you'll see I've got my pretty colors lined up, because that makes me happy. And a friend, a support squirrel. And, gather your stuffed animals and your fuzzy blanket or your favorite shoes or your, the most delightful fruity drink you have so that we can approach these problems hopefully lightheartedly. If word problems start to frustrate you, take a break. Don't spend more than a half an hour with any problem. Take a break, look at it again. If you really feel stumped, there's no reason to just push yourself through it. Take a break and send me a note. Say, hey, I'm struggling with this problem in 2.6, or send a note to a tutor. Get set up with some tutoring, ask friends, family, ask people on the street, have a math party. And so the goal would be at the end of this section that you have a really consistent way to approach a very particular type of problem that comes up actually quite a lot. So why is it a mixture problem? Well, generally speaking, a mixture problem is going to be any problem where we take two things and we bring them together in a mixture. So let's look at this first one. This is an investment problem. This is about an investor who wants to receive $1,000 annually from two investments. So basically, he wants to put money in the bank and then earn interest. So the money in the bank will slowly earn interest. And then he's going to come and grab the interest, but leave the original money in the bank. And so every year, interest will grow and he'll grab the interest, and then he has the original amount, that's called the principal, will still be in the bank. So every year it grows interest, every year he takes the interest and leaves the principal. So why is this a mixture problem? Well, if you'll notice, it says he has put $4,500 in a money market account paying 4% annual simple interest. And he wants to know how much should he invest in a stock fund that pays 10% annual simple interest to achieve his goal. So as you can see by the little chart I created, which you do not have to use, charts are optional. They help some people, they annoy some people. I have no way of knowing which of you will think they're great and which of you will think it's annoying. So all I can say is if this doesn't work for you, skip it. Go directly to what we do down here with the equations. But if you notice in the chart, we've got the money market and the stock fund. And so what he's going to do is going to take the money from the money market and the money from the stock fund and mix them together. So that's why this is a mixture. Now you might ask, well, is it possible to have more than two things mixed? Absolutely. There are problems as far as you want to go in math or engineering or economics or finance or a lot of other fields. They might not be mixing two things. They might be, and here I need a friend, but imagine there's another person. They might be mixing three things. So you see three hands, or four things. So these type of problems can be expanded to apply to a lot of different situations. So this is really a great foundational bit of work. So this is not for naught. I know a lot of times word problems feel like they're just random and useless, but this core type, the mixture problem, this will continue being useful as long as you're in math or many related fields. Okay, so let's actually sit down and look at it. So I got my colored pens, and I'm going to start off with the investor wants to receive $1,000 annually. Annually is very important. That's going to be really important. $1,000 annually from two investments. Okay, he put $4,500 in a money market account which pays 4%. So the money market pays 4%. So I'm going to do that in blue. Annual simple interest. Again, the word annual. Annual means every year. Let me see, I'll write it right here. Annual equals every year. How much should he invest in a stock fund? So the stock fund, I need another color. The stock fund pays 10%. Now, a lot of times people will look at this and go, wait a minute. So you've got the opportunity to earn 10%. Why would you bother with 4%? And the basic agreement, and it's not always true in the real world, but the basic agreement for economics and finance, and when we're doing these investment problems in math, is that the higher the interest rate, the higher the risk. And so if he invests everything in the stock fund and suddenly something terrible happens, like, I don't know, a quarantine and the stock market just takes a sudden dive, he could lose all of his money. So what you do is something called diversification. You put a little over here and a little over here. And you put up with the fact that this is a lower interest rate because it provides you with a lot more stability. So this is, low and slow, and this is fast and scary. This is the roller coaster. This is, the person driving very steadily in the far right lane. Okay, going the speed limit. This one's somebody racing in the fast lane. Okay, so first thing we need is a formula. And from the page of formulas, we have this one. It's the interest, which was simple interest, was principal times rate times time. Now you'll notice that for my chart in the top row, I've written this backwards. I did principal times rate times time equals I. And this is, I know it looks funny, this is an I, it's a capital I. So we've got P times R times T equals I. Okay, nice. And then I've got a whole row for the money market and a whole row for the stock fund. Now, if I had other amounts of money, like he was also investing in, I don't know, vacuums for whales, you would give yourself another row. So for each different investment, you'll have a separate row. So let's go through and reread the problem and get all the information from the money market. So the money market was the blue one. So this is the blue information. So do we know how much money he's put into it? The principal, the money that goes in. Money that goes in. Does we know? And if we look through, it says he has put $4,500 in a money market account. Woohoo! So I'm going to put $4,500. And then it's paying 4%. That's our interest rate. But the thing is 4% is a percent. We need to convert it to a decimal. So I'm going to convert it to 0.04. Okay. And for the time. Now, I'm going to come back to this. An investor wants to receive $1,000 annually, 1 year. And that comes from the fact that he wants it annually. These two are pieces of information from the blue, the money market account. He wants to do it for 1 year. Now, do we know how much interest he's going to earn from this? No, but we do have a formula. And generally speaking, most of the charts we're going to work with are going to be set up so that as you move across the chart, you're going to multiply. See how these are multiplication? So 4,500 times 0.04 times 1. 4,500 times, and I'm going to put it in parentheses because of the decimal point, 0.04 times 1. Now, again, I tend to emphasize my multiplications. You don't have to. When things are right next to each other, they just multiply. Okay, so then I can actually figure that out because there's no variables in there. That's all numbers. So 4,500 times 0.04 times 1. Now, I don't have to write in the times 1 because we know that's not going to change it, but it's just good habit. And that's going to give me oh my goodness. If you notice, you guys can see it. I can't. I was going to say, that's a weird amount of money. I typed in, sorry about that, 0.14. Well, this is a good opportunity to point out that when you're estimating, I know 4% is about 1/20th, right? 5% is exactly 1/20th. 10%, right? 10% of 4,500 is 450. So since this is less than 10%, it should be less than 450. So when I got that answer of 630, I was like, ooh, I probably made a mistake. Okay, let's try that again. 180. That seems about right. So he's going to earn $180 off of this investment. Okay, let's go to the stock fund. The stock fund is the pink one. Now let's see what information we have. Well, right off the bat, it says 10%. So I'm going to go right in here to the rate. That's 10%, 0.10. And that was in the pink. And we also know that this is 1 year because everything is being done annually. And the problem is, though, I don't see what I put here. He says, how much should he invest in a stock fund? So in other words, we need to know what goes there. And if we were in class, I'd ask you for what variable you want to use. I'm going to go ahead and assume it's X. A lot of people like to use X, and X is fine. Eventually, I'm hoping I can convince you to branch out, maybe use P, or maybe even use the first letter of your name, unless your name is Xavier, in which case you're set. But we're going to need that variable. But even with the variable there, to find the interest earned, I'm still going to multiply across. So I've got X times 0.10 times 1, which if I multiply all this together, I get 0.1x. Let's take a look at that. Okay, so I know the interest I earned from the first, and I know the interest I earned from the second. It's going to depend on how much, right? I don't know exactly how much it is because I don't know how much I'm going to invest, but I'll get that much interest left. And we want to know what? How much should he invest in the stock fund to achieve his goal? Now, where was his goal? His goal was up at the top. An investor wants to receive $1,000 annually from the two investments. So what he wants is the money market interest plus the stock market or the stock fund interest should be $1,000. That's what he's hoping for, right? That's how much money he's hoping to get right there. And I realized that I should separate that. So let's make that green and yellow. So it's not just green there. There's too many greens running around. So the money market interest is 180. The stock fund interest is 0.1x, and we get 1,000. So there's our equation. And now we can solve this equation. Before we do, I want to point something out. With a mixture problem, because we're bringing the two things together and combining them, generally speaking, excuse me, squirrel, I gotta use that space right there. Generally speaking, what you can do is you can take these results right here and add down. So 180 right there plus 0.1x is our total. So remember, when you go across, generally speaking, the formulas we're going to be studying are all multiplicative. So you multiply going across, you add coming down. These very particular types of problems. And I find it's helpful if you don't just memorize the steps, but sometimes it can be really helpful to memorize a rhythm or a pattern, almost like a dance. So if that can help you multiply across, add down. Okay, so I got my equation here, either by reading this or by going multiply across and add down. And again, some of you, if you do not like doing charts, that's fine. You met us again here. So you would have had to do a lot of this in your head and come to here. How can I solve this equation for x? So what am I going to do? I'm going to first take the 180 and subtract both sides, right? Minus 180 on both sides. Woohoo. Okay, I get 0.1x equals, I don't trust my brain. My brain is an awesome brain, but sometimes it reverses things or gets confused. So I always double check. I think I get 820, which seems about right. Now you've got two choices here. You could either divide by 0.1, which is fine, or you could multiply by 10. And I just want to show you this because I think it's kind of cool. A lot of people always think about dividing and they forget about multiplying. So I've got, let me write down exactly what I did here. I had 10 times 0.1x equals 10 times 820. So 10 times 0.1x is just x. And over here, 10 times 820 is 8,200. So for me, for my class, you can get away with just telling me x is, and make sure you include the units, 8,200. If you were in someone's class who wanted a sentence, you would have to say, he should invest 8,200 in the stock fund. Now, as far as I'm concerned, when you set up the chart, you have already declared what the x is. Now, if you skip the chart, you should be telling me, what does x represent? You should actually say x is how much he invests in the stock market. But again, if you set up the chart, I think it's very clear. Everyone can see what your x means. Kind of woohoo. Now, here's the thing about checking. You can certainly check your equation. So we could always check the equation that says 180 plus 0.1x equals 1,000. 180 plus 0.1 times 8,200. Is that equal to 1,000? This is 180 plus 820. That's equal to 1,000. Oh, yay! So we can check the equation. However, the one thing that's really hard to check about a word problem, one of the things that makes people very nervous, is that word problems, you have to come up with the equation. That was actually the hard part. Solving the equation was the short part. That was easy. Setting the whole thing up was the hard things. And there's not really a good way, especially when you're starting out, there's not really a good way always to check the problem itself. This is why I don't require that you check your equations, because you might have other mistakes in your word problem. But you certainly can. You can double check the equation, so you at least know, even if this was not the correct equation, I do know that this is the correct answer to this equation. Woohoo. Okay, having said that, I'm going to peek to see what was the next problem I wanted to do. Okay, we can go ahead and do this one. I am hopeful that this will go well. We will see. We're going to do a slightly different one. This is a uniform motion problem. And this is another one of the formulas that we came across. And it is distance equals rate times time. And I remember, you may remember from the formula page, I think of the equals as being an E. So this is D-E-R-T, dirt, which is how I remember it. But you can come up with another mnemonic if you'd like. Distance equals rate times time, or sometimes people just call it a rate time problem or a distance rate time problem. There are lots of ways to remember it. These are going to come up a lot, especially every time we're applying to physics, because physics is really interested in the position and the speed and the velocity, the acceleration, all that fun stuff. So we're going to go ahead and start off with this and talk a little bit about what the heck uniform motion. So the question is, uniform motion, does that mean that somebody is like dressed up in a uniform and is moving? And the answer is no. Uniform motion means averages. What the heck does that mean? Well, if you're driving a car, from the moment you get in the car, when you turn the car on, in that moment, you're not going anywhere. Most people do not start a car and have it move immediately. In fact, that's usually very dangerous and not a good idea, right? You turn on the car, you remove the brakes, you put it in gear, and then you go. And you go exactly the same speed the whole time. No, you slow down and start back up if there's traffic, for stop signs, for stoplights, all the different things that happen depending on what road you're on. You might drive really fast on one road, and on another road, it's got a much lower speed limit. However, this level of math is going to require that we think it's one level, one speed for the whole thing. So the actual car, the actual motion might look like you start at 0 and then you get going fast and then suddenly have to stop and then you speed up and you speed up again and then you stop. And uniform motion. So uniform doesn't just mean the outfit you wear. It means that you make everything the same. Uniform means the same. So in other words, in uniform motion, we would take this, and I'll make uniform motion be blue. And what we would do is we would set an average, and we would pretend the whole time we went the same speed. Rather than starting from 0, speeding up, slowing back down, speeding up, slowing back down, we would just say the whole time we went 25 miles an hour. Instead of sometimes it was 0 and sometimes it was 50 and sometimes it was 70, if that makes sense. So for this class, we have to stick with uniform motion. We have to stick with the average. We figure out what the average speed is. So when I say, how long will it take a mother running at 4 feet per second? Does it mean that the mother always moves 4 feet per second? No. It's starting and stopping and speeding up and slowing down. We just can't do that much in the math we have. So with the math we have, we're going to have a much more simple situation. Same thing with the toddler. She has to catch up with her toddler running down the sidewalk at 2 feet per second if the child had a 5-second head start. So this problem is a little bit terrifying if you've ever been a parent or you've ever been asked to care for somebody's kids. I will tell you, toddlers seem really slow, tell you look away, and then suddenly they're across the street and you're panicking. So let's take a look at what happens with this. How long will it take a mother running at 4 feet per second to catch up with her toddler running down the sidewalk at 2 feet per second if the child had a 5-second head start? So what's going to happen is the kid, the toddler, little kid, just starts going, right? He's running away. He sees like a puppy or something. There's like, okay, it's not a puppy because I can't draw a puppy. This is totally a cat. There we go. Cat. So the little toddler sees a cat and goes running towards it. Now, the mom, who's a really good mom, but she just looked away for 5 seconds. 5 seconds. So somebody said something. Someone yelled something, and she looked over. And when she looked back, she was like, oh no. And then she runs twice as fast. She runs 4 feet per second. The toddler is running at 2 feet per second. And if the child had a 5-second head start, how long does it take for the mom to catch up? So the first question I would ask is, can the mom catch up? And the answer is yes. Why? And the reason why the mom can catch up is that the mom, let's go with the mother. Here's the mother. The mother is running at 4 feet per second, and the toddler runs at 2 feet per second and has a 5-second head start. So the toddler is actually going relatively slowly compared to the mother. So what is the formula I'm using? Well, I'm using the distance equals rate times time. How do I know this? Well, because it's written on the page, right? But also I've got feet per second. That's distance per time. I'm talking about catching up. I'm talking about how long, that's time. 5 seconds, that's time. So anytime you start seeing speeds and times, we've got distance equals rate times time. So in my top row, just like with the previous one, I took my distance equals rate times time, but I wrote it backwards. Rate times time equals distance. So this is a multiplying. This one's shorter though. It's just 2 things multiplied together give me distance. Okay, so what does it mean when someone catches up? Let's see if I can do this. So it means we've got the 2 of them starting in the same place, and the toddler starts to wander. And the mom's looking around. She's like, "What? Did you say something?" And then she looks back and she's like, "Oh no!" And then she goes faster. And what does it mean that they catch up? What's the one thing that happens? Let me do it again. Here goes the toddler. It's a kitty. And then the mom's like thinking about something, or she's like, I don't know what happened to my 20s. I don't know. And then she's like, oh no. And then she goes twice as fast and catches up. And the thing that is the same is they end up, even though they go at different rates and at different times, they end up in the same place. So when the problem says catch up, it means the distances are the same. Okay, so let's look at the mother. The mother, R is the speed, that's the per. The speed is the per. 4 feet per second. 4 feet per second. And it doesn't say how long she was running, so I'm going to go down here to the toddler. The toddler was going at 2 feet per second. So far, so good. Now, this is where things get exciting. Does the toddler run for 5 seconds? Because it looks like, I underlined it in pink, it says 5 seconds. Does the toddler run for 5 seconds? And the answer is no. The toddler had a 5-second head start. So the toddler goes first, and then the mom goes, oh no, and catches up. So they're actually, for 5 seconds, just the toddler's going. And then for the rest of the time, they're both going. So it's not just 5 seconds. Can I suggest that if you use T for the mother, don't panic, you use T plus 5 for the toddler? What do you think? Because the toddler goes for 5 seconds more. So these are seconds. What do you think? Now, there is another school of thought that says let T be the toddler and let the mom be T minus 5. And you could do that way. I think it's a lot harder, so I'm going to do it this way. Now, remember when we did other problems? In the first one, it was all money, so it was easy. But in this, we got a lot of different things running around. So we should check the units. Feet match with feet. Good. They both have to be in feet. Feet per second, excellent, they match. Seconds match. So what is the distance going to be measured in? You're right, it's got to be measured in feet. It has no other choice. If this is feet per second and this is seconds, this has got to be feet. So now do we see anything about how far they get? And the answer is no, we don't know. However, we do know that if I take the 4 times the t, that will give me the distance, right? 4 times t, so this is 4 times t. Now this one's a little more, oops, This one's a little more exciting because this one's 2 times the quantity t plus 5. Remember, the toddler was running for 5 extra seconds. So we've got the mother's distance right there, and we've got the toddler's distance right there. So if they're going to catch up, the distances are the same. So the mother's distance equals the toddler's distance. So this is, I'm giving you an example. Anytime you have two things going in the same direction and one's going to catch up with the other, this is exactly how you do it. So this is one type of problem. Now, does this count as a mixture problem? It does, because it's going to follow the same rules. We're multiplying across. But do I add here? And the answer is no. I actually take the mother's distance, which is 4t, and I set it equal to the toddler's distance, which is 2t times the quantity t plus 5. Okay. So first thing I can do is I can go ahead. I'm grabbing another piece of paper because I know I'm going to need it. I can, if I'm going to solve this, I can multiply out. I'm going to use my distributive property, and I'm going to get 4t equals 2t plus 10. And then I'm going to copy that onto this page. 4t equals 2t plus 10. And then I'm going to solve from here. So I think I'm going to move the t's onto the left because the 4t is greater than 2t. So you know what the mathematician's favorite ice cream is? Tutti Frutti? Remember, we're subtracting 1 2t on each side of the pen. Okay, I'm sorry, that was a terrible joke. Ooh, I've got another one. What's the mathematician's favorite Shakespeare quote? 2t or not 2t? That is the question. Terrible? Okay, never mind, I'll stop. Okay, so I subtract the 2t, so I get just 10 over here. Now what am I going to do to both sides? You got it. Divide by 2. Hopefully this solving equation stuff is getting more second nature for you. Now, the tricky thing here is knowing what the heck to do with this answer, because we got t equals 5, and that's measured in seconds, right? And so is that the answer we're looking for? So let's look at the problem and see. How long will it take a mother running at 4 feet per second to catch up with her toddler running down the sidewalk at 2 feet per second if the child had a 5-second head start? So I got t equals 5. Let's look at my chart. Where does the t go? This t, where's t in the chart? It's right there. And in fact, that is how long the mother had to run. So the interesting thing is the kid started running for 5 seconds, and then the mom had to run another 5 seconds to catch up, which is interesting. And I bet that has something to do with the fact that the mother was going exactly twice as fast as the toddler. So the mom had to run for 5 seconds. This is not the best way to write it. I probably would have said it will take 5 seconds for the mom to catch up before she caught up with the toddler. And again, you do not have to write out a sentence. You can just put the box around as long as you've got the units. Now, what I would like to try to do is I would like to try to describe what's going on to show you why this makes sense. Toddler, mom. Okay. So the toddler two, 4, 6, 8, 10, 12, 14, 16, 18, 20. I lied. The little circle goes there. And I will make that look pretty. I was going to try to make it, there it is. Make it look pretty now. Magic. Okay. So what happens for the first 5 seconds? For the first 5 seconds, remember the toddler is running. 1. In 1 second goes, because the toddler runs 2 feet per second. So in 1 second, 2 feet. 2 seconds, 4 feet. 3 seconds, 6 feet. 4 seconds, 8 feet. 5 seconds, 10 feet. So this is where the toddler is when the mom goes, oh no. Now, how fast does the mom go? The mom runs by 4s. And this is how it's going to work. So let's see, 12, 16, 20. So in the first 5 seconds, the mom does not move. Mom is sitting there. The toddler's way over here. Now, in the 6th second, the mom goes 4 feet, because it's 4 feet per second. So in the 6th second, the mom goes to 4, and the toddler goes another 2. In the 7th second, the mom goes another 4, and the toddler goes another 2. In the 8th second, the mom is catching up, and the toddler goes another 2. In the 9th second, the mom is right on the toddler's heels at 16, but the toddler has gone just a little bit further. And in the 10th second, the mom runs to 20 feet, and so does the toddler. And so they end up at the same place, because the mom is taking much longer steps, and the toddler's doing little steps. Woohoo! Okay, you guys made it through a super long video. I think a lot of the word problem videos are going to be super long just because it takes a long time to explain these. So I would encourage you to go take a break, rest your eyes, close your eyes, go look at something green, maybe do some exercises, some stretches, get some water, and then come back and we will keep working on word problems. Woohoo! You guys are awesome and amazing. Math on, guys. Math on.